Hi. What we're going to do now is we're going to take the same code from the previous video. So if you haven't watched that first video, you should definitely watch it now. And what we're going to do is we're going to introduce assumption violations of the linear regression model into the Monte Carlo simulation. I'm going to use the exact same code as before, so I'm not going to spend time going through it, but I'm going to make some small changes. So just pay attention to what those changes are so you can replicate them yourself. So the first one I'm going to deal with is a specification error. So suppose that, in fact, the population regression model does not describe y equals a constant term plus x, but y equals a constant term plus x cubed. This is still a linear model because remember that the assumption is that the model is linear in its parameters. It doesn't have to be linear in its variables. But here we've specified that the relationship, the coefficient 3 applies to x cubed. What if we don't apply that to our understanding of the sample regression function? Will that produce unbiased estimates of beta 1? So what I'm going to do is I'm going to run the exact same code as before, and what we're going to see just at the end is what the simulation produces in terms of coefficients on the constant term and on x. And we can see how they differ after we've made this change to the functional form of the population regression equation. Okay. What we see here is that there's a high degree of bias in terms of beta 1, whereas beta 0, the constant term, this is still a pretty unbiased estimator of beta 0. Remember, in the population equation, beta 0 is 2. But beta 1 is about 9, whereas in the population regression equation it was 3. So this should illustrate for you why it's very important to think critically about what the true functional form of the population regression equation is. Often it's a very good idea to do some scatter plots of XY relationships before you start doing regression analysis, because simply the spatial pattern of that data might suggest to you the proper functional form of your model. The next assumption violation I'm going to look at is a situation where the error term, the expected value of the error term, is not 0. Keep in mind this is a critical assumption that goes into our model. If you have a situation where it's not just that the expected error term, the average error term, is not 0, but in fact the error term is correlated with x, you can get introduce serious bias into your model. But what I want to deal with now is just a more simpler situation where x and y x and the error term aren't necessarily correlated, but what we have here is a situation where the normal distribution of the error term is not centered around 0, rather it is centered around 3. And we'll look at how that affects our estimates of both beta 0 and beta 1. So again, all that I've changed here in this code is just added +3 to the code for u, which just tells Stata that rather than centering the distribution around 0 as is its default, and as we would expect given our assumptions, we're centering it around 3. Okay. Here we see that our estimate for the constant term is biased. However, our estimate for the coefficient is not biased. This is because while the error term, the expected value of the error term here is 3 rather than 0, we haven't said that the error term is correlated with x, which would be a critical problem likely brought on by omitted variable bias. By just saying that the error term is centered on 3 rather than 0 and not specifying that it is correlated with the error term, we're saying that the error term is only correlated with that portion of our model that is fixed and not a variable. The portion of our model that is fixed is the constant term. Hence, we have a biased constant term that is biased by exactly +3. which was the bias that we specified in the error term. Now, this is not a critical problem because in political science and social sciences in general, we're more interested in the effect of X on Y in the variables we're interested in rather than the constant term. So introducing bias into the constant term is not very critical. Indeed, if you review the earlier video on interpreting bivariate regression, you can see that in many cases, the constant term produces a nonsensical substantive interpretation. However, cases in which the error term is not equal to 0 but is not correlated with X are relatively rare. A more critical concern for us as social scientists is when we have something in the error term that we haven't controlled for that is systematically exerts an effect on X, is correlated with X, and is also correlated with Y. Then we would introduce a serious degree of bias to our estimates for beta 1, which ultimately, theoretically, would be the effect that we're interested in. But that problem of omitted variable bias and specification error is something that we'll revisit later in the course. All right. Thank you.